All right, now, so we are continuing with Taylor and MacLaurin series. This is part two. After we saw how do we present a function as a polynomial using, as an infinite polynomial using Taylor series, today we are going to approximate function using Taylor series. What do we mean by that? Let's start that section. So we are approximating function by using Taylor series or even MacLaurin series, but in which way? This is what we're going to do in the remaining part of this section. All right, we learned that any function, as long as it is differentiable like f of x, this f of x can be written as what? As a Taylor series in this form. And the expansion, if you remember, it's f at a plus the next one is f prime at a over 1 factorial times x minus a to the 1. So we started with n equals 0, we got this term, and then we continue, right? So f double prime at a over 2 factorial times x minus a square, right? So we're going to continue, guys, till we reach to the nth term. So this is going to be what? The nth derivative at a times x minus a to the power n over n factorial. Do we stop here? No, we have to proceed. What do we say? So the next term is what? Fn plus 1 at a times x minus a to the n plus 1 over n plus 1 factorial plus, of course, plus the plus goes all the way to infinity. This is an infinite series and never stops. All right, how do we approximate a function? Means I'm going to find the value of the function at a certain point. Like I will ask what's f of 3? Given that f like a ln function or sine function, cosine function, whatever function is. So if I give you ln x, f of x equal ln x, can you tell me exactly what's ln 3? Yes, we can. How do we do that, guys? First, we're going to change the function into what? Into polynomial, but not infinite polynomial. I will do the following, guys. We are going to cut this series and just take what? The first nth terms. So those are the first nth terms in the Taylor polynomial. What do I do with the rest? Nothing. The rest of that, I'm going to call this one a remainder, r, n of x. You know it's a function of x. The first n terms in this polynomial, I'm going to call it the nth Taylor polynomial. Okay, guys? So I'm going to call the first n terms in the Taylor series the Tn polynomial, Tnx polynomial, which is the nth Taylor polynomial, and the leftover is Rn, and this is called the remainder. Okay, R means the remainder. All right. By the way, this remainder, if you take the first n terms in the series to approximate the function at a certain point, this remainder is going to be so small that it is what? Ignorable. You can just ignore it. Okay. But here in this section, I'm going to show you how small this remainder is. Okay. This is why we ignore it. So what does this lead actually? So we can say that our function f of x can be approximated by what? So we can write as this Tn of x, the first Taylor series, nth Taylor series, plus what? The remainder. Right? We can write the function like this. The first n terms in the Taylor series plus the leftover, which is called the remainder. In other words, we can say that my function f of x is now approximately equal to what? To Tn of x. Why? Because I just mentioned to you that the remainder is so small that it can be what? Ignored. So what do we say? Now we don't say that f of x is equal to Tn. So now we can say the function f of x can be approximated using the first n terms in Taylor series. So it's not equal to, but it's approximately equal to the what? To the first n terms in Taylor series. And this is, guys, what we're going to do in this section. And what we're going to do also, we are going to see how big the remainder is. We are going even to approximate the remainder. Okay. And this is what we have in the second part. So Taylor series, I took the first, this is what we call, this one is Tn of x, as you see. Those are the first n terms in the polynomial. So this is our Tn. So accordingly, we said that the function f of x can be written as the first n terms in Taylor polynomial plus what? Plus the remainder. This remainder is called the error. As I said also, it's so small that it can be ignored. All right. The question is, how can I really find how big is the remainder or the error after I chop it? When I take the first n terms, there is something left, right? The leftovers are Rn. This Rn, how big it is, or what is the maximum value that this Rn can take? I can approximate this one in three ways. The first way is by graphing the function Rn. And of course, graphing is impossible. Or let's say I don't have the machine to do that. So I'm gonna, this one, completely ignore it because it's not really convenient. So the first method will not be used. What if the first Tn polynomial or our Taylor polynomial, Tn that I found, is an alternating polynomial, like plus minus, okay? If it's an alternating polynomial, then the remainder or the error, the absolute value of the error, is going to be less, it's not gonna exceed what? The next term in what? In our Tn polynomial. What's Bn plus 1? Bn plus 1 is the n plus 1 in the Tn polynomial. Means this is exactly, I'm gonna go back here, guys. You see this term here? This is the n plus 1 term. This is going to be our Bn plus 1. And the remainder, the error is not going to exceed this value. So everything else will be almost zero. So this is the upper bound for remainder. If the series here is what? If this Tn is alternating series, then the remainder is going to be no more than this value and everything can be ignored. Okay, that's something we know, we have to know. Second thing, what if Taylor series was not alternating series? If in all cases, whether it's alternating or not alternating, we can use this method. But if it's alternating, we can use method number 2. I will show you this in examples. What if the Taylor polynomial, the nth Taylor polynomial is not actually alternating? Then I have to go to the third case here. What does it say? It says the following. The remainder, the error, should not exceed m over n plus 1 factorial times x minus a to the n minus 1, where x will be given to us that it is somehow between so and so. So when x is between c and d, here is x is between c and d, then I can approximate this one using this formula. The question is, what is m? M here is an upper bound of what? Of the n plus 1 derivative of the function. Where again, x here is also between c and what? And d. This looks tedious, not understandable, but we will see it once we go to the example. But in case, we're going to focus on two cases. If the Tnth polynomial, Taylor polynomial, the first n polynomials that we're going to find is alternating polynomial, then we can say the bound for the error will not exceed what? The n plus 1 term in the remainder. Okay, if it's not alternating series, then the remainder or the error should not exceed this value. Okay, where n is what? Of course, n depends on what? Remember, what's n? N is depending on which Taylor polynomial we're talking about. So n is known, a is known, n is known here. So what's left is m. What's m? M is the upper bound of the n plus 1 derivative. When x is between c and d, you will be given x a value between c and d. I will show you this. I think examples are going to show everything and explain everything I just said in this part. Here's an example, guys. Let's start this example. It says approximate the function f of x equal cube root of x by a Taylor polynomial of degree 2 at a equal 8, then use it to approximate this. So by the way, we know that the cube root of 8 is what? Is 2. Can you tell me what's a cube root of 8.1? No, it's not possible. So what I'm going to do here, I'm going to use Taylor series to approximate the cube root of 8.1. So let's start part A, guys. Look what he wants. This is our function, first of all. F of x is equal to the cube root of x. What does he want to find? He says approximate the function of x using what? A Taylor polynomial of degree 2. So he wants to find T2 of x. This is what he wants, the second Taylor polynomial, where at a equal 8. All right, so what's T2 of x, guys? T2 of x is the Taylor series where I equal 0 to 2. Remember, what's Taylor? Fn of a times x minus a to the power I over I factorial. By the way, I'm going to change this one to I. Remember, it was Taylor, it was n, but I'm going to change it to I and make my count from 0 to 2. So this is the second Taylor polynomial. And let's expand it, by the way. So it's like expanding any Taylor polynomial. So what's the first? Remember, in Taylor, the first one is f of a. Plus, what's the second one? Now, I'm done with I equals 0. When I is equal to 1, remember, what was it? It was f prime at a times x minus a to the power 1 over what? 1 factorial. Now we go to the second one, which f double prime at a times x minus a square over 2 factorial. This is, guys, this is what we call the second Taylor polynomial. Only the first two terms, but in when n is equal to 2, that means there will be 3 terms always, because the first one is 0, by the way. The count is from 0, so 0, 1, and 2. Okay, what's a here? A in the question is 8, so I need to find f of 8 plus f prime at 8 times x minus 8 to the power 1 over 1 factorial plus f double prime at 8 times x minus 8 to the power 2 over 2 factorial. This is our second degree polynomial. Remember from the previous in the Taylor series, what do we look for, guys? We are going to look for f of 8, f prime of 8, and f double prime of 8. To do this, let's go back to our function. What's f of x in the question? It's the cube root of x, which is actually x to the 1/3. Now, what do I need to find? F of 8. What's f of 8 equal to? It's 8 to the 1/3. And by the way, 8 is what? Is 2 cubed, right? 8 is 2 cubed to the power 1/3. But when you have a power raised to a power, what do? You multiply the powers. So 3 times 1/3, they cancel, and the answer is 2. So we got this to be 2, guys. Now let's find f prime of 8. Okay, what's f prime of x? Here is fx, by the way. So the power goes down. Then you reduce the power by 1. 1/3 minus 1 is minus 2/3. And this is equal to 1 over 3 x to the 2/3, right? We can bring the negative down. Now let's find f prime at 8. What's the answer? 1 over 3, then 8 to the power 2/3. And this is 1 over 3. Remember, 8 is 2 cubed to the power 2/3. 3 goes with the 3. So you have 2 square. 2 square is 4. 4 times the 3 is 12. So the answer is 1 out of 12. So now we got f prime of 8, guys. Now we find f double prime of x. This is f prime. So if I differentiate this again, it's going to be what? 1/3 times minus 2/3 goes down. Then x to what power? Minus 2/3, and minus 1 is minus 5/3, right? So minus 5 over 3. And this is equal to, this times this is minus 2 over 9. And then we can bring this one down, which is x to the 5 over 3. And this is equal to negative 2 over 9. Okay, so my apology here. We have to plug 8 now. So let's go back and erase that one. So now I have f prime. So this implies that f double prime at 8 is equal to negative 2 over 9 times 8 to the 5/3. And this is equal to minus 2 over 9 times 2 cube to the 5/3. What happens? 3 cancels 3. So you have minus 2 over 9 times 2 to the power 5. 2 to the power 5 is 32. So 32, let's take the calculator and see what do we have in all of this. Oh, actually, so this is actually negative 2 over 9 times 32. This one with this one is 16. So 16 times 9, I think it's 144, if I'm not mistaken. 16 times 9, yeah, it's 144. So the answer is minus 1 over 144, guys. This is the second derivative at 8. Before I start computing T2, or let's find T2 here. So T2 of x, the second Taylor polynomial, is the first term, remember, was 2. So it's a 2. The second term is 1 over 12, so plus this one, f prime at 8 is 1 over 12, and 1 factorial is 1, so this is 1 over 12 times x minus 8. Minus, this one is 1 over 44. f double prime is 1 over 44, so this is 1 over 144 times 1 over 2 factorial, which is 2, times x minus 8 square. Let's simplify this one. So it's 2 plus x minus 8 over 12. Now 144 times this, I think it's 288. So minus x minus 8 to the power 2 divided by 288. This one now, guys, is T2 of x. This is, so I just approximated my cube root function of x into a second degree polynomial. Now, what does he want? He wants to compute this, isn't it? He wants to find the cube root of 8.1. So what I'm going to say, by the way, okay, so this is an approximation. So we can say, by the way, so our function f of x, so what do we conclude? Therefore, our function f of x, which is the cube root of x, is approximately equal to what? 2 plus x minus 8 over 12 minus x minus 8 square over 288. This is, guys, the approximation of the function using the second Taylor polynomial, and almost the first part A is done. What's left is to find the cube root of 8.1. Let's go to the next page. What would be then? He wants to find the cube root of 8.1. What is this equal to? Now remember that the cube root of x is approximately equal to 2 plus x minus 8 over 12 minus x minus 8 square over 288, right? This is what we know from the approximation. Now, so this implies that the cube root, so the cube root of 8.1 is approximately equal, I'm going to plug it here. So it's 2 plus what? 8.1 minus 8 divided by 12 minus 8.1 minus 8 square divided by 288, which is equal to 2 plus 8.1 minus 8 is 0.1. 0.1 is 1 over 10, right? So it's going to be 1 over 120, because this is 1 over 10, and there's 12 at the bottom, so 1 over 20. Minus. This is also 0.1, but when you square it, it will be 1 over 100. So this is 1 over 28800. Okay, this is the value of the function at 8.1. This is the approximation of 8.1. And if you compute this one using your calculator, if you like, I think you will get something like, this is all the computations here, and it's almost 2.0082. 2.0082. So this is 2.0082. I can say approximately 2.008. This is the approximation of 8.1, guys, up to 4 decimal places. So part A is completely finished now. Let's start part B. He wants to know how accurate is this approximation when x is between 7 and 9. Remember, I'm doing this at 8, right? So here's 8, by the way. Here's 8 in part B. I need to approximate the function. Okay, I did approximate, so I got this one. For x between 7 and 9, if x is between 7 and 9, so I'm going to go 1 unit before 8, because you know this series is convergent at 8. So but 1 step before 8 and 1 step after 8, what do you think is the maximum bound for the error? So what does he want? He says, how accurate is the approximation? So that means he wants to find R2 of x is less than what? This is what he wants to know. The remainder, remember, there is remainder. I just took the first 2 terms, guys. There is what? Third, fourth, fifth, all the way to infinity. So there is still infinitely many numbers. I need to find the leftover. Remember, I said the leftover is almost what? Ignorable, because it's going to be too small. I'm going to show you how small it is. So let's find how much is the error. The formula says, remember the formula says that Rn of x, the upper bound, is less than m divided by what? N plus 1 factorial times x minus a to the power n plus 1. This is the upper bound for our remainder, our error, where this m is what? An upper bound of the n plus 1 derivative. N plus 1 derivative is bounded by m. And I'm going to compute all of this when x is between 7 and 8. All righty? So this is what we need to do. So to find this, the first thing you have to find, guys, is m. I'm going to start by this m. So let's see what m is. Let's focus on m. M here is an upper bound of the n plus 1 derivative. Okay, guys. So here, let's talk about R2. So that means I'm going to say R2 of x is less than m over, I'm going to put 2 here. So 2 plus 1 factorial times x minus, remember a in the question is 8, times 2 plus 1 to the power 2 plus 1. That means R2 of x is bounded above by m over, this is 3 factorial, which is actually 6, times x minus 8 to the power 3. So let me write it again. So R2 of x is bounded by m over 6 times x minus 8 to the power 3. This is the bound of my function. Okay, so I'm going to go to the next page and say that R2 of x is bounded by m over 6 times x minus 8 to the power 3, where, don't forget that x is between what? Between 7 and 9. Okay, so let's see what happens here, guys. When x is between 7 and 9, let's look at this value, guys. What is the maximum this can reach to? To do this, look at this. X is between 7 and 9. I'm going to subtract 8 because you see inside the absolute value of x minus 8. So what happens when I subtract 8 here? Then that means I have to subtract 8 here which means I have to subtract even 8 here. So this will lead that x minus 8 is less than equal, 9 minus 8 is 1, and greater than with what? Negative 1. Do you know from absolute value, when x is between a and minus a, this is the same thing as saying that the absolute value of x is less than a. I don't know if you remember this. This is what it means for the absolute value of x to be less than equal. It means it's between a and minus a. So look at this, x minus 8 is between 1 and minus 1. What does that mean? That means the absolute value of x minus 8 is less than 1. So this is what we have, guys. So the absolute value of x minus 8 is less than 1. But it has a cube here. So I'm going to cube this. So x minus 8 to the power 3 is less than equal to 1 to the power 3, right? I cube both sides. But we know that 1 to the power 3 is 1. So what am I going to say here? So this is less than or equal to m over 6 times what, guys? This one is 1. So, right, all of this less than 1. So all of this less than or equal to 1. So which is equal to what? M over 6. So what do we say here? So that means R2 of x is less than or equal to what? M over 6. Now, let's find the m, guys. If I have the m, I have the solution. I know what's the upper bound here. Now, don't forget that m is an upper bound of the n plus 1 derivative. So let's go back here. Don't forget that. Where did I write it down? I wrote it down somewhere here. Where? Yeah, here it is. M is an upper bound of the n plus 1 derivative. So, but n in the question is 2, right? So I'm going to find that. Now let's find f to the n plus 1 of x is less than, it says less than m. Now, since n is equal to 2, so I'm going to find f what? Third derivative of x. I'm going to find an upper bound of the third derivative of x. Right? What's the third derivative of x? Let's go back and look for the second derivative of x. Where is the second derivative of x? The second derivative of x was this one. So I'm going to copy it down. Minus 2, or I can say minus 2 over 9x to the minus 5/3. So I'm going to copy it down and say, but which is equal to absolute value of, sorry, here is this, minus 2, oops, sorry, I'm going to write it here. So the second derivative of x is equal to minus 2 over 9x to the minus 5/3. Just to check it again, minus 2 over 9x to the minus 5/3. This is correct. This is exactly the second derivative. Let's do the third derivative, guys. What's the third derivative of this? It's minus 2 over 9. Now this power goes down, becomes here, minus 5/3 goes down, times x to what? Subtract 3 from this. This is going to be minus 8/3. This times this is 10/27. And this x to the minus goes down. So this is x to the 8/3. So this is going to be 10/27 x to the what? 8/3. This is the third derivative of the function. Okay, let's do the trick again, guys. What's the trick? The trick says that x is between 9 and 7. Let's look at the third derivative. What do I have? X to what power? 8/3. So I'm going to take this x and raise it to the power 8/3. So that means it's going to be 9 to the power 8/3 greater than to 7 to the power 8/3. I took the power of 8/3. But notice here that x to the 8/3 is down, is not up. Here it's up. So I'm going to flip it. So 1 over x to the 8/3 is going to be greater than, when you flip it, you have to switch the inequalities. So this is 1 over 9 to the 8 over 3 less than or equal to 1 over 7 to the 8 over 3. It's 10 over 27. So now I'm going to multiply 10 over 27 x to the 8 over 3. In the middle, I multiply the middle by 10 over 27. So I have to do it here. 10 over 27 times 9 to the 8 over 3 less than or equal 10 out 27, then 7 to the 8 over 3. All right, now I need the derivative, guys, to be less than, not greater. So you see, I need it less. Where is less? So this is the derivative. By the way, this is the third derivative. I need it less than. So I'm going to look at that. And I'm going to trash this one. I don't want it to be greater. I want it to be less than. So I need my third derivative to be less than. So this is less than or equal to what? 10 over 27 times 7 to the 8th third. And if you do this by calculator, you find that this is as small as 0.0021. This is the upper bound of the third derivative. So look what I'm going to do now, guys. So now I'm going to go back to this here. So I'm going to say, look at M. So this is, by the way, capital M. This is our M. So this is equal to 0.0021 divided by 6. And if you do this, you will end up with 0.0004. Look how small my error is. So this is, guys, the maximum error. So you see, I took that second Taylor polynomial, only the first 3 terms in Taylor polynomial. How many terms left? Infinitely many, which is the fourth, the fifth, the third, the fourth, all the way to infinity. All of those, they are as small as 0.0004. So imagine if I approximated the function using the first, for example, 5 Taylor polynomial. So I use the fifth. Do you know how much is the error going to be? You need, even though there are infinitely many, it's going to be almost 0. So this is the magic of using Taylor. So if, imagine, I just only took T2 and the remainder is as small as 0.0004. So really, this is a good thing. So I can say, actually, if I go back to my answer, what was the answer, by the way, when we approximated the function? What was the answer of the approximation? The approximation is where, here it is. So when we approximated the function, we got this, right? So we can say here, guys, that the cube root of 8.1, so the cube root of 8.1 is approximately equal to what? 2.008 plus 0.0004. And this is equal to 2.00. If I added this 0 to 8, I will get 8,4, right? So 8 and 4. Just very small and minor error. So this is exactly how much it's going to be by using the calculator. Okay, so this is the value of the cube root of 8.1. It's around 2.0084 because I found the error to be 4. All right, so this will be the best answer for the question. Okay, let's do now another question. This is the solution for what I just did. Okay. Here's another function, another question. I have the function f of x equal x ln x. I need to approximate it using Taylor polynomial of degree 3. Now, so 3. So what I have here in part A, guys, we know that f of x is equal x ln x. He says, find the third Taylor polynomial of this one. At a equal to what? At a equal to 1. Okay, that's easy. What do we say? We say that T3 of x is the sum of the first, where I equals 0 to 3 of what? Of our Taylor. Our Taylor says it's Fn, or let's say Fi of a here is 1, times x minus a, which is 1, to the power I over I factorial. This is exactly the third Taylor polynomial. And remember that third Taylor, the first one we always know it's f of a, which is f of 1. The second one is f prime at 1 times x minus 1 over 1 factorial plus f double prime at 1 times x minus 1 square over 2 factorial plus f triple prime of 1 times x minus 1 cube over 3 factorial. So those are, guys, the first 3 terms in Taylor polynomial. And how many we have? We have 4 terms because we're starting with I. So T3 has 4 terms, not 3 terms. What's our work now is to focus on finding those values, this one, and this one. All right, what do we start with? We start with our function f of x. What's f of x here? It's x ln x. This implies, guys, if you plug 1, what do we get? We get 1 ln 1. But we know that ln 1 is 0, so the answer is 0. Ln 1 is 0. Now let's differentiate the function, guys. F prime of x. What's the derivative of this? You know, this is a product of 2 functions, so it's the first times derivative of the second, which is 1 over x, plus the second, which is ln x, times the derivative of the first. The derivative of x is 1. And so this is equal to, this x goes with this x, and you have 1 plus ln x. This is the first derivative, guys. Now let's find the value of the first derivative at 1. It's 1 plus ln 1. We know that ln 1 is 0, so this is 1. So now we are done with this term. Now let's find f double prime. F double prime of x is what? We are here. The derivative of 1 is 0. The derivative of ln x is 1 over x, so we get 1 over x, which implies that f double prime at 1 is 1 over 1, which is 1. Finally, f triple prime of x is equal, we know the derivative of 1 over x is minus 1 over what? X squared. So that means f triple prime at 1 is equal to what? Minus 1 over 1 squared, which is negative 1. So far, so good. This is what we have. So now here, I'm going to say, therefore, T2 of x is equal to, f of 1 is a 0. F prime of 1 is 1. So plus, this is 1, guys, over 1 factor, which is 1. So I'm left with x minus 1. F double prime is also 1. So this is 1 over, so plus x minus 1 square over 2 factorial is 2. Plus f triple prime. F triple prime is minus 1, so we're going to say minus x minus 1 cube over 3 factorial, which is 6. So this is T2. So what do we say, guys? So that means the x ln x, our function x ln x, is approximately equal to what? X minus 1 plus x minus 1 square over 2 minus x minus 1 cube over 6. So I was able to approximate this x ln x as a third degree polynomial, as you see it here. Okay. Then he says approximate f of 2. By the way, this is f of x. This one is f of x. So to find f of 2, what do? We say it's approximately equal to what? We're going to replace this with 2. So it's 2 minus 1 plus 2 minus 1 square over 2 minus 2 minus 1 cube over 6. And this is equal to 1 plus half minus 6th. The least common between those is 6, I believe. 6 divided, so we're going to multiply by 6. So this is 6 plus 6 divided by 2 is a 3 times 1 is a 3 minus 1. 6 plus 3 is 9, minus 1 is 8 over 6. And this one is 4 over 3, guys, which is 1.3333. So that means, what do we conclude from this one, guys? So f of 2, which is 2 ln 2, is nothing but 1.333. You see, we found it without calculator. So part A now is finished. Now let's go to part B. To go to part B, guys, we need to do the following. What does he want? He says, now how accurate is the approximation when x is between this and this? Remember, we did the third Taylor polynomial, so I need to find the third error, R3. What's R3? Less than m over n plus 1 factorial is 4 factorial times the absolute value of x minus a here is 1 to the power what? N plus 1, which is to the power 4. And this is equal to m over 4 factorial, by the way, is 4 times 3 is 12 times 2 is 24. So this is 24 times x minus 1 to the power 4. Right? So now this is what we know. So we know that the error will never exceed m over 24 times x minus 1 to the power 4. Now look, what are we given here? So let's start here. He says x in the question is between 0.5, which is half, and 1.5, which is 3 halves, right? This is the value given to us. Let's compute this, only this. So I'm going to subtract 1 from both sides. So x minus 1 is less than 3 half minus 1 greater than half minus 1. That means x minus 1 is less than, now 3 half, which is 1.5 minus 1 is half. Here, half minus 1 is minus half. Same as we did before. That means the absolute value of x minus 1 is less than half, right? Because it's between half and minus half. That means the absolute value is less than half. But I have absolute value to the power 4. So that means x minus 1 to the power 4 is less than half to the power 4. But half to the power 4 is 1 to, sorry, to the power 4, my apology, to the power 4. It's 1 to the power 4 over 2 to the power 4. 1 to the power 4 is 1. 2 to the power 4 is 16. So we have the absolute value of x minus 1. I hate to erase, but I had to sometimes make some minor errors. So the absolute value of x minus 1 to the power 4, guys, not 8. This is 4. This is why I'm doing this mistake. It's 4 to the power 4 is less than 1 over 16. So I'm going to go back here and say this is less than m over 24 times 1 over 16. So this is what's the error. So what's left is m, guys. To find m, remember, m is the upper bound of the n plus 1 derivative. So I'm going to find now f to the 3 plus 1 derivative of x is having an upper bound of m. M is an upper bound of what? Of the n plus 1 derivative. N here is a 3. So that means, so this implies that m is the upper bound of the fourth derivative of the function. Okay, let's do here the third derivative. What was the third derivative of the function? Let me go back and figure out what did I get. I got minus 1 over x squared. So this is minus 1 over x squared, which is minus x to the minus 2, right? I put it up. So that means the fourth derivative will be the derivative of that minus 2 goes down. So it's minus 2x to the minus 3, which is equal to 2 over x cubed, guys. So this is the fourth derivative. So therefore, the fourth derivative of x which is equal to 2 over x cubed is less than m. Now, how do I figure out what m is? Okay, let's take our x, guys, in the question. Again, x is between half and what? And 3/2. We're going to follow the same strategy. In the derivative, what do I have? I have 2 over x cubed. So I'm going to cube this x. So x cubed is, the cube of 3 is 27. The cube of 2 is 8. So this is less than 8, greater than or equal to, the cube of this is 1 over 8. Now, what do? We flip it because we have 2 over x cubed. So 1 over x cubed is greater than or equal to 8 over 27, less than or equal to 8 over 1. I'm flipping everything. All right, but in the derivative, it's 2 over x cubed. So I'm going to multiply by 2 now. So 2 over x cubed is greater than or equal to 16 over 27, less than or equal to 16. Who is this one, guys? This is the fourth derivative, isn't it? And so the absolute value of that is less than the absolute value of 16. And what's the absolute value of 16? It's 16. So that means, therefore, the fourth derivative of x, which is equal to 2 over x cubed, is less than what? 16. Who is this 16? This is our m. So what do I do now? I'm going to go back here and say the following. So my error, the third error, which is of the third Taylor polynomial, is less than what? M, which is 16 over 24 times 1 over 16. This 16 goes with this 16, so I have 1 over 24. So this is, guys, the upper bound of my error. It's almost 1 over 24, which is a very small number. This is the upper bound of my error. And this solves actually part B. All righty. So question number 10. He says, approximate the function f of x equal x cosine x by a Taylor polynomial of degree 3 at a equal to 0, guys. So part A says f of x is equal to x cos x. So far, so good. He wants to find the third Taylor polynomial at a equal what? 0. So what does that mean? He wants to find the MacLaurin series, isn't it? Right? He wants to find the MacLaurin series at a equal to 0. So to find this one, guys, let's think of cosine x. Remember cosine x? What's the MacLaurin series of cosine x? If you go back to what we did last time, guys, the table I gave it to you, right? We know that cosine s is presented as -1 to the n, then x to the 2n over 2n factorial, where n equals 0 to infinity. Who's this? This is the nth MacLaurin series of cosine x. Remember that? This is the nth MacLaurin series of cosine x. We found it last time. Okay, but our function f of x is not cosine x, it's x cosine x. So if I multiply this by x, what do I get, guys? So this is n equals 0 to infinity -1 to the n, x to the n over 2n factorial times what? Times x. So I'm going to multiply this by x. Same Taylor, same MacLaurin, just multiplied by x. When I multiply it by x, what do I get? I'm going to get the sum of -1 to the n over n, 2n, sorry, factorial. Look, this is x to the power 1. What happens when I multiply it? Don't we just add the powers? So this is x to the what? 2n plus 1, where n equals 0 to infinity. So this one, guys, is the MacLaurin series for x cosine x. So I'm going to write it down. So x cosine x is nothing but the sum of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n factorial. Who is this? This is the infinite series, MacLaurin series of x cosine x. But I need only T3, the third degree. So what's T3 of x, guys? So it's going to be the sum where n equals 0, only to what? Not I even, not n. We say I equals, you change I to n to I, up to 3 of negative 1 to the I over 2I factorial times x to the 2I plus 1. All right, so let's expand it. Let's start with 0, guys. Minus 1 to the 0 is 1. 2 times 0 is 0. 0 factorial is 1. Put a 0 here. 2 times 0 is 0. Plus 1 is what? Is x. So the final thing is x. This is when I is equal to 0. Now, let's put I equal to 1. What do I get? Plus minus 1 to the 1 over 2 times 1 factorial times x to the 2 times 1 is 2 plus 1 is what? Is a 3. Plus, let's put I equal to 2. So what do I get? Minus 1 square over 2 times 2 is 4 factorial times x to the 2 times 2 is 4 plus 1 is what? Is 5. Now the last one is a 3. Let's put a 3. It's minus 1 to the power of 3 over, now 2 times the 3 is 6 factorial times x to the, put the 3 here, 3 times 2 is 6 plus 1 is what? Is a 7. Let's simplify this. So this is x. Now minus 1 to the 1 is minus 1 over 2 times 1 is 2, 2 factorial is 2. So in the top, so this is x cubed over 2, right? Here, minus 1 square is plus x to the 5 over, you can actually make this one, keep it as, no, let's make it, okay? Now, so this is positive. 4 factorial is 4 times the 3, which is 12 times 2 is 24. So this is 24. Now, minus 1 to the 3 is negative x to the 7 over 6 factorial, 6 times 5, which is 30, 30 times 4. So let me maybe use the calculator here, or I can just leave it as 6 factorial, but I'm going to find it actually. What is it exactly equal to? So let's say 6 factorial is 720. All right. So this is, guys, the presentation of the third Taylor polynomial or third MacLaurin polynomial of x cosine x. I'm done with part A. All right. What do we notice here, guys? We notice that this is what? Alternating series, right? This is alternating series. All right. Do you know what's the next term? Okay, so because it's alternating, so now continue. We're gonna find R what? R3 of x, upper bound. The formula says, case number 2 says, if the series is alternating, so this is less than equal. I don't have to find m on all of this. It's less than what? Bn plus 1, which is b or what? N here is a 3, so b4. So the upper bound is less than the fourth term in the polynomial. Let's go back, guys, and see what's the fourth term. What do you see the fourth term from here? If this is 2 factorial, so the first one is 2 factorial, 4 factorial, 6 factorial. So what's the next term going to be? I'm expecting the next term to be what? Positive x to the 9 over what? Over 8 factorial, right? I shouldn't have actually changed the factorials. So probably to be more accurate and get a better answer, I'm going to bring everything back to the way it was. So I'm going to put it this way, 10. So it's x, then this is 2 factorial. The next one was 4 factorial, and the next one was 6 factorial. So 3, 5, 7, then definitely the next term is 9. power 9. Since 2 factorial, 4 factorial, 6 factorial, so the next one is 8. And since alternating plus, minus, so the next one is that. So this one actually is our B for x9 over 8 factorial. So this is, so that means the third one is less than x to the, what did we say, sorry, x to the 9 over 8 factorial. This is the upper bound. Here, he did not give me what x is. So this is all I can do here. He did not give me an interval. So now I'm going to go to part B. It says, find the value of x that makes the approximate accurate to within this. So he wants to find x such that this error, which is x to the 9 over 8 factorial, is somehow less than 0.00002. This is the upper bound he's looking for. He wants to find x such that this error does not exceed this value. So what do I do now? I'm going to multiply the whole factorial, the whole thing by 8 factorial. So that means x to the 9 is less than 0.00002 times 8 factorial. Take the 9th root. So x is less than the 9th root of 0.00002 times 8 factorial. And if you use the calculator here, you will get 0.98. So that means x, guys, has to be 0.98 in order for the error not to exceed this number. So that means I'm going to approximate the function, which is what? X cosine x at what point? At 0.98. Meaning what? Meaning 0.98. Look at here. Cosine 0.98. Okay, if I did this one, the error of that one, the error R3 of x, okay, will not exceed what? 0.00002 whenever what? When x is what? 0.98. So if I put this one, the error will not exceed this value. Okay, this is the answer for this question. And this, guys, summarizes everything you do here. So in this part, we are approximating the function using the nth Taylor polynomial, and we are approximating the maximum error that happens after I take the first n polynomial. Remember, there are plenty of terms after that, but those terms are so small, and I was able to approximate how big is that error after the nth Taylor polynomial. I hope you like it. This is the end of our Taylor and MacLaurin series. All right. So now we can go and finish the chapter of the last section of this chapter in the next video. You guys have a good day.